we're going to tie some ideas together a little bit today. So first off, if I want to factor x squared plus 5x plus 6, I could guess and check it, or I could find the two numbers that multiply to 6, add up to 5, and then factor by grouping. I'm just going to guess and check it real quick. X plus 3 times x plus 2 is what that factors into. So if you think about how like factors relate to division, that means if I was to divide x squared plus 5x plus 6 by x plus 3, I would get x plus 2 as a result, because those two original things multiply together to get you it. We are going to use a new technique of division and then work on some more complicated factoring today. So our division that we're going to use is called synthetic division. It is a little bit of a shortcut algorithm instead of long division, but it only works for certain polynomial division problems. So you have to be dividing by something that has a coefficient of 1 on your variable. So you could divide by like x plus 1 or x plus 2, but not by, say, 2x plus 1 or 3x minus 4. Those you would have to use long division on. Okay, so how's this synthetic division thing work? How it works is you are going to make sure you aren't missing any terms. So like long division, I'm going to put a placeholder in for 0x to the first, and then I'm going to write those coefficients down. Now I'm going to figure out what makes what I'm dividing by equal to 0. So I'm going to find the 0 for my factor of x minus 3. That would be x equals 3. I'm going to take that value that makes it equal to 0 and put it kind of on the outside here. So that'll be 3. And then it's kind of like the long division algorithm. First, though, I'm going to drop down my first number and then multiply it back times the number that was on the outside. So 2 times 3 gives me 6. It's kind of like when you multiply back in long division. Then you're going to add those two values together. So 9 plus 6 gets me 15. I'm going to multiply that new number back. 15 times 3 gets me 45. Again, add 0 plus 45 gets me 45, and then multiply back again. 45 times 3 gives me 135. 5 plus 135 gets me 140. So that's just a string of numbers. It's not really my answer or my result of my division problem. So what you need to think about is, well, my original polynomial, I was doing 2x to the third divided by something that was x to the first. So that means I'd have x squared as my degree on my first term, and then just decreasing my degree by 1 for each of the following ones. X to the 0, remember, is just like a 1 equal to 1, so that's just my constant. And then my last value is going to be my remainder, 140 over what I was dividing by. So some vocab reminders. Factors of an expression are what you multiply together to get your original. So if you think about like our warm-up one, that had factors of x plus 3 and x plus 2. The zeros of that polynomial are what make the polynomial equal to 0, so that would be -3 and -2. And then factor theorem kind of says that, hey, if you know that you have a factor, then whatever makes that factor equal to 0, if you plug that into your expression, you get 0 out. And reminder, multiplicity of a 0 is the number of times it appears in your polynomial. Okay, so we're going to use our division skills to factor some polynomials that are higher degree. So we're going to divide by the factor that we know and see what result we get. So I'm going to divide 2x cubed minus 11x squared plus 3x plus 36 by my known factor of x minus 3. And I'm going to use that to rewrite my original expression. So if you do your synthetic division here, just run through it real quick, you're going to end up with 2x squared minus 5x minus 12. And now if you're thinking about what our original expression equals, our original expression equals what we got times what we divided by. Kind of like if you divide x squared plus 5x plus 6 by x plus 3, you get x plus 2. So you know your original expression equals those two values multiplied together. For ours, we divided by x minus 3 and got that as our result. So our original equals x minus 3 times 2x squared minus 5x minus 12. So we're supposed to factor this completely, which means if 2x squared minus 5x minus 12 factors further, we need to factor it further. So I'm going to factor by rewriting my middle term here and using grouping, looking for numbers that multiply to 2 times negative 12, negative 24, and add up to negative 5. I'm going to have to run through a few here. There we go. Negative 8 and 3. That is how I'm going to rewrite my middle term. And then I'll use some grouping, factor out a common factor from my first two terms, from my last two terms. So I can factor out a 2x, leaves me with x minus 4, and then factor out a 3, also leaves me with x minus 4. So my final completely factored version is going to have my factors of 2x plus 3, x minus 4, and the one I divided by x minus 3. So that would multiply together to equal my original expression. You could try it. You'd end up with what we had to start with. Okay, so if you want to check your part B, it should have ended up like that when you factored it completely. Now we can use that work to find the zeros of our polynomial. You could possibly rewrite it if you want to as x plus 4 to the second. If we're trying to figure out what makes those equal to 0, look at what makes each factor equal to 0. We get negative 4 and positive 1. And our multiplicity of our zeros matches how many times that factor shows up. So negative 4 has a multiplicity of 2, and 1 has a multiplicity of just 1. So if you've done the work to rewrite it in its factored form, I've already done a lot of the work to find the zeros. This time we have a 0 instead of a factor given to us, but we can use that 0 to figure out a factor that goes along with it. So if 2 is a 0, 2 would make the factor x minus 2 equal to 0. We want to find the x-intercepts. Well, if we had it factored, we could set it equal to 0 to find our x-intercepts. So let's see if we can get it factored, because I can't really set this equal to 0 right now and just solve it using any of our equation solving skills. So this time I am given the 0, so make sure you use positive 2 on the outside, because that makes the factor that you know it goes with equal to 0. Well, our middle term ended up being 0x, and then plus 25, no remainder. So we got x squared plus 25 times our factor of x minus 2 is equal to our original expression. Now, if I want to find the x-intercepts of that expression, it's easier now to figure out where it's equal to 0 at. So if I set that equal to 0, then I'm going to end up with an x value equal to 2. And if I set x squared plus 25 equal to 0, I can solve it. But if I take the square root of negative 25, I'm going to get it plus or minus I. So the only x-intercept this graph has is at the point 2, 0. The other two zeros that it's got are non-real complex numbers, so they won't give us x-intercepts on our real valued coordinate plane that we're graphing on. So one important thing about those non-real complex zeros is that they come in pairs. So the conjugates of them are zeros. If you have like 2x plus 3i, and you know that that's a 0, that means that 2 minus 3i is automatically going to be known to be a 0 as well. And that applies to, if you think about like our 5i and our negative 5i that we got, 0 plus 5i, 0 minus 5i, those are conjugates, and both of them are zeros as well. So reminder, fundamental theorem of algebra says a polynomial of degree n has n zeros. So if we are looking at this degree 5 polynomial, it should have, according to the fundamental theorem of algebra, 5 zeros. Some of them might be real numbers, some might be non-real numbers. So if we count up how many we're given here, we're given 1, 2, 3 zeros. That means that I'm missing 2 more. So in this case, the conjugate zeros theorem is actually going to give me those 2 more zeros that I'm looking for, because I have a couple of complex zeros and their conjugates will also be zeros. So if you look at this one, if 5 plus 2i is a 0, then 5 minus 2i is a 0 as well, one that wasn't listed out for us. And same idea with positive 4i, it's like 0 plus 4i, 0 minus 4i, or negative 4i are zeros too. So those are our fourth and fifth zeros of our degree 5 polynomial that we were missing. So whatever the degree is, that's the number of zeros you should be able to find.